let's look at a new category of Sturm-Liouville problems. There are periodic Sturm-Liouville problems. They might have the same definition of an ODE as before. The only difference is that now the boundary conditions are mixing information at the two endpoints. So let's look at an example. This is minus y second equals lambda y. That is the same structure as before, but now we have introduced new boundary conditions. Well, we also introduce a new interval. We go from minus L to plus L, and we say that the value of y at minus L is equal to the value of y at L, and the same goes for the first derivative. So we're, in some senses, we're pasting the interval minus LL back together at the back. These periodic boundary conditions are not in the form that we usually require for the Sturm-Liouville problems. So we have to expand our Sturm-Liouville problem with a new category, periodic Sturm-Liouville problems. We should still check that the Lagrange identity holds in this case. So we define our operator h that goes from y to minus y second of functions that the self-adjoint, this operator, we haven't proved it's self-adjoint yet, goes from functions that satisfy boundary conditions to functions that satisfy boundary conditions. And we want to see if the Lagrange identity is satisfied. So if the inner product of f times h applied to g is equal to the inner product of g times h applied to f. So let's compute this. Let's compute the inner product of g times hf. Then it's the minus the integral from minus L to L of gf second dx. And by integration by part, this is minus gf prime computed between minus L and L plus the integral going from minus L to L of g prime f prime. As you see, g prime f prime is symmetric, so we can switch f and g, but the first term with the boundary conditions is not, but the periodic boundary condition imposed that both g and f prime need to be 0, both at minus L and at L, so this is trivially 0. We can compute the inner product of f times hg, and we retrieve the same thing. So h is a self-adjoint operator, also in this case of periodic boundary conditions. We can make boundary conditions non-zero, non-trivial, but the result will still be the same. H would be a self-adjoint operator. But all the theory we have looked at when we were looking at Sturm-Liouville problems all depends on the fact that H is a self-adjoint operator. That is, that the Lagrange identity is satisfied. Now that we have proven that the Lagrange identity is satisfied, H we have proven is a self-adjoint operator even when we have periodic boundary conditions, then all the spectral theorems that we have seen still apply in this case. So we can look at this problem and look for a general solution of the eigenvalue problem. If we assume lambda is equal to 0, then the only solution that we have is that y is a first-order polynomial, but it wouldn't satisfy the boundary conditions, so this cannot be. I just realized that a equals b should have to be equal to 0, but a can be non-zero, and we would satisfy the boundary conditions, but we're going to loop back to it later. Then we look at lambda different than 0. Then we have y satisfying a characteristic equation, and we can write y as a sine kx plus b cos kx, where we define k as the square root of lambda, or k squared equals the absolute value of lambda. Let's say lambda positive, because of the periodicity of sine and cosine. Which lambda can we choose in order for yx to be non-trivial while respecting the boundary conditions? So we do the usual trick. We apply the boundary conditions on the two both on y and on y prime. This time we have to be careful because they are on the two different points. But luckily sine and cosine are one is odd and one is even, so having them computed part at L and part at minus L just means that some negative signs pop up. We simplify some terms, then we retrieve two equations. 2a sine kl equals to 0 and 2kb sine kl equals to 0. This gives us three options. Either sine kl is equal to 0, or a equals to b equals to 0, that is the trivial solution, not very interesting, or k is equal to 0. If k is equal to 0, then everything is 0, except that b can be non-zero. So we would have a solution that is the constant 1. So we have the constant eigenfunction that loops to the previous options, the trivial solution that is not interesting and we're going to throw away, or sine kl equals to 0. Let's assume k different than 0 because we have taken care of that already. Then sine kl is equal to 0 gives us kn equals n pi over L. Notice that it's the same that we retrieved before with non-periodic boundary conditions. So, but this time it appears both in the cosine and in the sine. So we have yx being a sum of cos knx plus sine knx for any coefficient in front of these two terms. This means that we can split this as two eigenfunctions associated to kn that are linearly independent, the cosine knx or the sine knx, and they're orthogonal. That means that the inner product over minus L to L of the product of these two is equal to 0. So they are indeed completely linearly independent eigenfunctions. So if f is periodic with period 2L, then we can write f as a sum of a0, phi 0 is the constant function equal to 1, times plus an infinite series of an sine knx plus bn cos knx. This is called the Fourier series. And we can compute a0, an, and bn as we did compute all the other coefficients in the other cases. Notice that this time we did not renormalize things. So an, for example, is equal to f times sine knx, inner product between the two, divided the norm of sine kx squared. So the inner product of sine kx times sine kx. The same is true for a0 and bn. Well, they kind of share the same function, the same formulas. We could compute the normalization of the eigenfunctions. We have to do it anyway because we want to compute the values an and bn. So we want to compute the inner product between the eigenfunctions that we have found. So sine knx times itself, inner product, or cos knx times itself. Somehow the integrals have switched their values. I'll correct the slides when I give it to them. So obviously the inner product of sine times sine is the integral of sine np over lx squared, and the inner product of cos is the integral of cosine. So we call one of them I and the other j, and we claim that they are the same thing if you change the variable from x to y equals x plus L. On top of that, we have that the integral from minus L to L of cos squared plus sin squared. Well, cos squared plus sin squared is equal to 1, so this simplifies to the integral from minus L to L of 1 dx, that is 2L. So we have that both I and j have value L. So the normalized eigenfunctions are 1 over square root of L sin knx and 1 over square root of L cosine knx, and phi 0 also should be normalized, so it's 1 over square root of 2L.